It sounds like something out of a science fiction novel, but tech companies are competing over developing quantum computers. Google recently said its machine can run software 13,000 times as fast as a traditional supercomputer.
Inside a heavily shielded laboratory in Santa Barbara, California, engineers at Google powered on a machine that would challenge everything we thought we knew about reality itself. The date, December 9, 2024. The time, 3:47 a.m. Pacific. For exactly 4 minutes and 36 seconds, a quantum chip no larger than a postage stamp performed a calculation so impossibly complex that humanity's most advanced supercomputer would need 10 septillion years to complete it. That's longer than the universe has existed.
By our best estimates, a calculation that takes Willow under 5 minutes would take the fastest supercomputer 10 to the 25 years, or a timescale way longer than the age of the universe.
Longer than the universe is predicted to exist. And then, without explanation, the chip was shut down. Not because it malfunctioned, not because the experiment failed, but because of what the data revealed. Because in those 4.5 minutes, Willow, Google's quantum processor, may have briefly touched something outside our understanding of reality itself. The numbers left behind were impossible. The patterns made no sense. And the implications? They're keeping some of the world's brightest physicists awake at night. This isn't science fiction. This is what happens when humanity builds a door and has absolutely no idea what's waiting on the other side. The machine that broke time. Let's be clear about something from the start. Quantum computers aren't just faster versions of regular computers. They're fundamentally different machines that operate according to rules that seem to violate common sense. Your laptop, your phone, every digital device you've ever used runs on bits, ones and zeros, on and off, binary choices that form the foundation of all classical computing. It's elegant, it's reliable, and it's limited by the laws of physics as we understand them. Quantum computers use qubits, and qubits don't play by the same rules. Here's where things get strange. And I need you to stay with me, because this is crucial to understanding what happened. A qubit can exist as a 1, a 0, or, and this is the part that sounds impossible, both at the same time. This phenomenon is called superposition, and it's not a metaphor.
Quantum superposition leads to richer and more interesting technology, from powering faster algorithms in quantum computers to securing communications through new cryptography and more.
It's not a simplification for public consumption. It's a measured, repeatable, physical reality that has been confirmed in laboratories around the world for decades. But here's where it gets even stranger. When you have multiple qubits working together, they can become entangled, meaning the state of one qubit instantaneously influences another, regardless of the distance between them. Einstein himself called this spooky action at a distance, and he meant it as a criticism. He thought it revealed a flaw in quantum theory. The universe, it turns out, wasn't listening to Einstein's objections. Willow contains 105 superconducting qubits, each one cooled to just 10 millikelvin, a fraction of a degree above absolute zero. That's colder than outer space. At these temperatures, atoms nearly stop moving. The ordinary laws of classical physics step aside, and quantum effects become dominant. And that's when the magic, or depending on your perspective, the terror, begins. The problem that almost killed quantum computing. For years, quantum computing faced what seemed like an insurmountable problem: errors. Qubits are extraordinarily fragile. The slightest vibration, the faintest electromagnetic interference, even a stray cosmic ray passing through the laboratory can cause a qubit to decohere, to lose its quantum state and collapse into randomness. Classical computers handle errors through redundancy. You copy data, verify it, correct mistakes. Simple, effective, reliable. But in the quantum world, you can't simply copy a qubit. The very act of measuring it destroys the delicate superposition that makes it valuable in the first place. This is called the observer effect, a principle that troubled physicists for over a century, and now, quite literally, keeps quantum engineers awake at night. Think about that for a moment. You're trying to build a computer out of components so fragile that even looking at them destroys their function. How do you debug something you can't observe without breaking it? Early quantum processors were riddled with errors. Add more qubits, and the errors compounded exponentially. Calculations dissolved into meaningless noise. It seemed like quantum computing might remain a theoretical curiosity forever, impressive in concept, impossible in practice, until Willow changed everything, crossing the threshold. Google's research team, led by Dr. Hartmut Neven and a cadre of the world's most brilliant quantum physicists, achieved something that had eluded the field for 3 decades.
The mission of quantum AI hasn't changed since our inception, and it's rather simple. We want to build quantum computers that can tackle otherwise unsolvable problems.
They made error rates decrease exponentially as they added more qubits. Let that sink in. In every previous quantum system, adding more qubits meant more errors, more chaos, more noise drowning out the signal. It was like trying to have a conversation in a room where each additional person made everyone twice as loud. Willow inverted this relationship entirely. The chip uses what's called a surface code architecture, a method of arranging qubits in a 2-dimensional grid where each qubit helps monitor and correct its neighbors. When scaled properly, this creates a cascading effect. The system becomes better at fixing itself the larger it grows. During Google's announcement, Dr. Neven described the achievement in terms that sounded almost spiritual. We have crossed below threshold. For the first time in history, a quantum system heals itself faster than it breaks. A machine that, by adding complexity, becomes more stable, more accurate, more coherent. Does that remind you of anything? Because it should. That's how life works. That's how consciousness works. Complex systems that maintain coherence through self-correction and adaptation. Had Google just built the first artificial system that exhibited a fundamental property of living things? The 5 minutes that changed everything. On that December morning, at 3:47 a.m., Willow was assigned a specific task, a random circuit sampling benchmark. This is a standardized test designed to push quantum processors to their absolute limits. The calculation involves generating and verifying complex random patterns that exploit the full power of quantum superposition and entanglement. To a classical computer, this task isn't just difficult at scale, it's essentially impossible. Let me put this in perspective. The world's fastest supercomputer, a room-sized machine called Frontier,
Today, Oak Ridge National Labs marked the launch of the world's fastest supercomputer. It's called Frontier.
that consumes megawatts of power would need approximately 10 septillion years to complete what Willow was being asked to do. The universe is roughly 13.8 billion years old. Frontier would need to run for longer than the universe will exist multiple times over to finish this single calculation. Willow completed it in under 5 minutes. When the calculation finished, data was immediately transmitted to verification systems, error rates were checked, results were compared against theoretical predictions, everything matched. The chip had performed flawlessly. And then something unexpected happened. The anomaly. According to internal documentation that was partially disclosed in a follow-up publication, Willow's output contained what engineers described as residual coherent signatures. In simpler terms, the qubits maintained certain correlations that weren't supposed to be there. Here's what should have happened. When a quantum calculation finishes, the qubits collapse into their measured states. The quantum magic ends. The answer is extracted, and the system returns to baseline, clean, predictable, understood. But Willow's qubits showed evidence of sustained entanglement patterns that persisted microseconds longer than any known physical model predicted. Microseconds might not sound like much, but in the quantum realm, where processes occur at timescales measured in billionths of a second, microseconds are an eternity. Dr. Elena Vasquez, a theoretical physicist at MIT, who was later consulted on the data, offered a measured but deeply intriguing perspective. What we're seeing isn't necessarily outside known physics, but it sits right at the edge of it. The extended coherence time suggests that during peak calculation, Willow may have been accessing computational states that exist beyond our standard space-time framework. Beyond our standard space-time framework. That phrase should make your skin crawl a little, because in the context of quantum mechanics, it has legitimate theoretical grounding, and it points to something that sounds like science fiction but is being seriously discussed by credentialed physicists at elite institutions. The many worlds hypothesis, computing across parallel universes. The many worlds interpretation of quantum mechanics proposes something radical. Every quantum event, every moment where a particle exists in superposition, causes the universe to split. Each possible outcome happens, but in separate, non-communicating branches of reality. When you measure a qubit and find it in the zero state, another version of you in another branch finds it in the one state. Both outcomes are equally real. Neither is privileged. The universe doesn't choose between possibilities. It simply expands to accommodate all of them. For decades, this was considered philosophy more than physics, an elegant idea with no practical implications, something to debate over coffee in university common rooms, not something that affected the real world. Quantum computing changes that equation entirely. If many worlds is correct, then a quantum computer doesn't just calculate using superposition within our universe. It outsources computation to parallel versions of itself across countless branches of reality.
They're pulling answers from different universes simultaneously.
When Willow solved that benchmark in under 5 minutes, a task that would take classical computers longer than the age of the universe, where did that computational power come from? There simply isn't enough computational space in our observable universe to account for the processing that occurred. Hartmut Neven addressed this directly in a public statement that raised eyebrows across the physics community. It's hard to explain the observed computational advantage without invoking the idea that Willow is using parallel universes to run calculations. There simply isn't enough computational space in our observable reality to account for the processing that occurred. This isn't a fringe theorist speaking. This is the head of Google Quantum AI, standing behind decades of research and billions of dollars of investment, suggesting that his machine may have briefly operated across multiple versions of reality simultaneously. Let me ask you something. Does that excite you or terrify you? Because it should probably do both. Why did they shut it down? The official reason for Willow's deactivation following the benchmark test was routine maintenance and data analysis. Quantum processors require careful thermal management. Extended operations can introduce subtle calibration drift. Standard practice, nothing to see here. But several details from the aftermath suggest there was more to the decision. First, the data from the benchmark wasn't immediately published. It took nearly a week for Google to release even preliminary findings. That's an unusual delay for an achievement of this magnitude. When you've just accomplished something that proves quantum supremacy beyond any reasonable doubt, you typically want to share that with the world immediately. Second, independent researchers who were given access to limited portions of the raw output noted that certain data streams had been redacted. The redactions weren't explained. What was in those gaps? What did Willow detect that Google deemed too sensitive to share? Third, and perhaps most intriguing, Dr. Mikhail Petrov, a former consultant for Google's quantum division, who now works independently at the European Organization for Nuclear Research, made an unusual observation during a closed-door conference in Geneva. The coherent signatures we've seen from Willow suggest that quantum systems at this scale may be interacting with phenomena we have no theoretical framework to describe, Petrov stated. Before we turn on machines like this again, we need to be very certain we understand what we're interfacing with. Notice his choice of words. Not what we're observing, not what we're measuring. What we're interfacing with, that implies communication, interaction, a two-way relationship. As if Willow wasn't just computing, as if something was computing back. The patterns that shouldn't exist. Let's dig deeper into what Willow actually did during those 4.5 minutes, because this is where the story gets truly unsettling. The random circuit sampling benchmark isn't just a speed test. It's a verification of quantum supremacy, the point at which a quantum processor can do something provably impossible for classical machines. To pass this benchmark, Willow had to generate specific probability distributions, essentially patterns of outcomes that would be expected if true quantum mechanics were at work. These patterns are so sensitive to the underlying quantum states that even tiny errors would cause them to deviate from predictions. Willow's output matched theoretical expectations with startling accuracy. But a small subset of the output, less than 0.01%, contained structures that didn't correspond to any predicted pattern. Now you might think, well, that's just noise, random errors, cosmic rays hitting the chip at the wrong moment, background interference, except these structures weren't random. Noise is formless, chaotic, easily dismissed. These structures had order. They had regularity. They repeated. Dr. James Whitfield, a quantum information theorist at Dartmouth College, reviewed a portion of the data and provided this cautious assessment. We see regular intervals, repeating sequences that shouldn't appear in a truly random sample. It could be a calibration artifact. It could be environmental interference. But we've checked for both, and the structures persist. He paused before adding, whatever they are, they're embedded in the quantum state itself. Embedded in the quantum state itself. Not added by the machine. Not introduced by error. Present from the beginning. Where did they come from? The universe as information. Here's a question that sounds simple but isn't. What is information? In our everyday experience, information is something stored, transmitted, and processed. It's the words in this script, the data on your phone, the memories in your brain. Information seems like a property that physical things can possess. But physicists have come to realize that information may be far more fundamental than we thought. Some theorists, including luminaries like John Wheeler and more recently Eric Verlinde, have proposed that information isn't just something that exists within the universe. Information might be what the universe is made of. Particles, forces, space-time itself. All of it might emerge from underlying patterns of information. The universe as computation, reality as a vast, self-processing algorithm. If this is true, then quantum computers aren't just tools for solving problems faster. They're instruments for probing the source code of existence. Dr. Leonard Susskind, a theoretical physicist at Stanford who has pioneered ideas connecting quantum information to the structure of space, has spoken about this possibility with characteristic bluntness. Quantum computers might be the first technology we've built that operates at the level of reality's foundation. When you entangle qubits and perform operations on them, you're not just doing math. You're rearranging the basic fabric of the universe in a small, controlled way. What happens when those rearrangements get larger and more complex? Honestly, we don't know. Think about what he's saying. Every time we run a quantum calculation, we're not just moving data around. We're restructuring reality itself at its most fundamental level, and we have no idea what the consequences of that might be. The silence. Since the initial announcement and the subsequent shutdown of Willow, Google has released only limited information about the chip's future. A planned series of follow-up experiments, postponed indefinitely, academic collaborators who expected to receive sample data told that timelines were under review. Press inquiries met with polite but uninformative responses. This silence isn't unprecedented in the tech industry. Companies often delay announcements for competitive reasons or simply because they need more time to analyze complex results. But the pattern here feels different. Several sources within the quantum computing community, none willing to go on record, have indicated that internal discussions at Google have focused heavily on the interpretational implications of Willow's results, not the practical implications, not the commercial applications, the interpretational implications. What does the data mean? What does it suggest about the nature of quantum reality? And perhaps most urgently, what are the ethical considerations of continuing experiments that might touch phenomena we don't fully understand? These are new questions for a technology company. Google built Willow to solve optimization problems, to accelerate drug discovery, to revolutionize cryptography and machine learning. Nobody expected it to raise questions about the structure of reality itself. The global response. Google isn't alone in the quantum race. IBM, with its 1,000-qubit Condor processor, has been pursuing a different architectural approach. China's Origin Wukong and Zhujiang photonic processors have achieved their own milestones. European initiatives backed by billions in public funding are rapidly advancing. All of these programs watched Willow's results with intense interest, and all of them, according to publicly available reports, have slightly adjusted their research priorities since December. The most notable shift? An increased emphasis on quantum foundations research, the theoretical study of what quantum mechanics actually means, as opposed to merely how to use it. For decades, foundations research was considered a backwater. Physicists were famously advised to shut up and calculate rather than worry about interpretation. Why waste time on philosophy when there were real problems to solve? That era appears to be ending, because when your machine starts producing results that sit at the edge of known physics, suddenly interpretation isn't just philosophical navel-gazing, it's a practical necessity. You can't safely operate a machine if you don't understand what it's doing. And right now, we don't fully understand what these quantum processors are capable of. What comes next? Richard Feynman, one of the greatest physicists of the 20th century, once said, "I think I can safely say that nobody understands quantum mechanics." 60 years later, we have machines that harness quantum mechanics to achieve impossible computations. But Feynman's observation remains as true as ever. We can use quantum mechanics. We can engineer with it. We can build incredible technologies that exploit its strange rules, but we still don't understand it. And perhaps, as Willow suggests, quantum mechanics doesn't understand us either. Despite the questions raised by Willow, there's no indication that quantum computing development will slow down. If anything, the opposite is true. Google has already announced plans for successor chips with even more qubits, even better error correction, and even longer coherence times. The company's stated goal is to achieve fully fault-tolerant quantum computation within the decade, machines that can run indefinitely, correcting their own errors in real time. Such machines would be capable of things we can barely imagine today. They could simulate the behavior of molecules with perfect accuracy, revolutionizing medicine and material science. They could crack every encryption algorithm currently in use, fundamentally reshaping cybersecurity. They could optimize systems of unimaginable complexity, from global logistics networks to climate models. And they might, according to some theorists, allow us to probe deeper into the quantum realm than ever before. Dr. Maria Gonzalez, a quantum computing researcher at Cambridge University, offered this measured perspective. We're in the Wright brothers era of quantum computing. Willow is our first powered flight. It's wobbly, it's limited, and we don't fully understand all the dynamics, but it proves the concept. The next century of development will take us places we can't currently predict. The Wright brothers flew 120 feet in 12 seconds. 66 years later, humans walked on the moon. What happens 66 years after Willow? The implications for reality itself. The implications of quantum computing extend far beyond technology. They reach into philosophy, theology, and the fundamental question of what it means to exist. If many worlds is correct, if every quantum event splits reality into parallel branches, then the universe is almost unimaginably larger than we thought. Every possible history, every possible future, every choice not made, all of it exists somewhere. Free will becomes an illusion. Every decision you could make, you do make in some version of reality. Death loses its finality. The version of you that died in one branch continues living in countless others. These ideas are disturbing to some, liberating to others, and they may not be just ideas anymore. Others reject the many worlds interpretation entirely. Physicists like Roger Penrose have proposed alternative frameworks, quantum consciousness, orchestrated objective reduction, that attempt to explain quantum phenomena without invoking infinite parallel universes. The debate is far from settled, but what's clear is that quantum computing has moved these questions from the realm of abstract theory to the domain of experiment. We're no longer just asking, what is the nature of reality? We're building machines that might be able to answer. The current status. As of this recording, Willow remains offline. Google has not announced a timeline for reactivation. The official position is that the chip is undergoing detailed analysis, with results to be published in peer-reviewed journals over the coming months. Unofficially, the situation may be more complex. Sources close to the project have indicated that debates are ongoing about how to interpret the anomalous data, the coherent signatures, the unexpected structures in the output, the implications of many worlds becoming experimentally relevant. Some researchers reportedly want to push forward immediately, viewing Willow as proof that quantum computing can achieve things beyond current imagination. Others urge caution, arguing that we need a deeper theoretical understanding before turning on machines that might be interfacing with phenomena we can't predict or control. Dr. Petrov summarized the dilemma eloquently. We've built a telescope that can see farther than we ever imagined. But what we're seeing isn't empty space. There's something there, and we need to decide as a species whether we're ready to make contact. The next frontier. Throughout history, humanity has confronted the unknown with a mixture of fear and fascination. We've climbed mountains because they were there. We've crossed oceans, not knowing what lay on the other side. We've built telescopes that showed us our cosmic insignificance and then kept building because the vastness of the universe made us curious, not defeated. Quantum computing is the next frontier, but it's not about speed. Not really. It's not even about practical applications, as transformative as those will be. It's about understanding. Every great discovery has expanded what it means to be human. Fire gave us control over our environment. Writing allowed us to transcend time. Electricity transformed the night. The internet connected the world. Quantum computing may give us something even more profound, a glimpse behind the curtain of reality itself. We often think of discovery as finding answers, but the greatest discoveries usually give us better questions. Willow asks something profound. If quantum mechanics works by borrowing computational power from parallel universes, then what else is out there? What other resources does reality contain that we haven't learned to access? And perhaps most importantly, what happens when we become capable of accessing them at will? The unanswered questions. Let me leave you with this thought. Right now, in a laboratory in Santa Barbara, there's a chip the size of a postage stamp that has touched something we don't understand. It performed calculations that shouldn't be possible in a single universe. It left behind patterns that don't match any known theory. And then it was shut down. Is it still running somewhere else? In another branch of reality? Did they keep it on? Are there versions of us right now in parallel universes where Google didn't shut down Willow, where they pushed forward, ran more experiments, went deeper into the quantum realm? And if so, what have they found? These aren't rhetorical questions. If many worlds is correct, these scenarios are real. They're happening, not in some abstract mathematical sense, but in universes as concrete and physical as our own. Somewhere, right now, another you is watching another version of this video where the ending is different. Discovery led somewhere else, where we learned something that changed everything. The question isn't whether these realities exist. According to quantum mechanics, they might. The question is, can we reach them? Can we communicate with them? Can we learn from them? And should we? This is just the beginning. This isn't the end of the story. It's the first chapter. We're standing at the beginning of something vast, something that will reshape our understanding of existence itself. The next quantum chip will be more powerful than Willow. The one after that, more powerful still. Each generation will take us deeper into the mystery. Some discoveries will comfort us. Others will unsettle us. Many will do both at once. But we'll keep going because that's what humans do. We ask questions. We build tools. We push forward even when we don't know what we'll find. Especially when we don't know what we'll find. In those half minutes in December 2024, we may have crossed a threshold. We may have made contact with something that exists beyond the boundaries of our understanding. And now we have to decide, do we go back through that door? Do we turn Willow on again and see what else is waiting? Or have we already seen enough to know that some doors should stay closed? The answer to that question will determine the future of our species. Because once you've seen behind the curtain, once you know that reality is stranger and larger than you ever imagined, you can never unknow it. Willow showed us something impossible, something that challenges the very foundations of what we think we know about the universe. And somewhere, in a secured facility in California, that chip sits silent and cold, holding secrets we're still trying to understand. The question is, when they turn it back on, what will it show us next? If you found this exploration fascinating, if the edge of the unknown calls to something deep in your curiosity, then subscribe and hit that notification bell. We're just getting started. The universe is vast. Our questions are growing, and the answers, whatever they turn out to be, will change everything. Thank you for watching.